Welcome back everybody, Mr. Allen here. Just going to take you through a quick run through of section 3.1 data analysis here. There's a lot in this section, a lot of words, so I thought maybe just kind of going through it would be helpful. So just as a start here, download, print, there's a summary sheet. If you open that up, you'll see some of the key concepts that are new to the first few sections. It doesn't necessarily cover everything we're going to see, or it certainly doesn't cover everything we're going to see, but it's a nice starting point for some of the things that will be new. A lot of this shouldn't be new, so again, just kind of running through it. A lot of terminology here at the top. This should have been review from the organization of data section. If it isn't, you may need to ask questions about it, but again, I think it's fairly straightforward if you've seen it before. You certainly should have. Population, just the word population in the context of statistics means everybody in the group that we're looking at. So the population of our class would be everybody who's a student in the class. The population of your school would be everybody in your school. The population of the province, of course, would be everybody in the province, and so on. It doesn't necessarily mean any one population. We're talking about the population in which we're interested. If we're interested in people who live on a certain street who own a certain type of dog, then that is the entire population. It could be a very small group. If the group is large enough, then we can take a sample of the group. Sometimes it's unnecessary and unreasonable to assume we're going to be able to talk to everybody in a population. So a sample is any subsection of the population. And I'll sort of state down here, provided a sample is well chosen and large enough and without bias. Bias is from that previous unit as well. Conclusions for the population can be inferred from the sample data. Meaning if I do a good job of choosing my sample, I make sure there's enough people in it and it is representative of everybody in the original population, then it's going to be fine to make conclusions about the overall group as well. A few other terms. Census, you probably know, but the census is when the entire population is studied. StatsCan takes a census every 5 years. A cross-sectional study is basically looking at various groups kind of in the moment. You survey a bunch of people and then you may want to compare how the grade 9s answered versus the grade 12s, these sorts of things. The teachers in your school versus the students in your school, and so on. You may also want to just collect data from all those groups for the sake of making overall observations. That's certainly possible as well. But it's sort of one time in the moment is the idea. The opposite of that is a longitudinal study where basically a group is surveyed over the course of probably many years or at least many weeks to determine kind of what effects we have on them or what effects certain changes perhaps to their lifestyle have on them. And the examples here are things like new workout routines and so on. So you might have one group doing a specific workout routine or taking certain nutritional supplements or following a certain diet, other people who are not, and then you can compare the two. But you watch them over the course of several weeks, several months to see how one group is affected by the changes you've made to their lifestyle versus those who haven't had those same changes. These two are probably not terms that were showed up in the previous section, but again, they should be pretty obvious, I think. Observational studies are basically researchers are standing back and observing the group. So the key here is they're not affecting the group or influencing them in any way. Experimental studies, and again, the fact that it says experiment right in it tells you that you're basically testing something. So researchers assign the two groups to assign members to different groups, apply some kind of quote-unquote treatment to the one group, a different exercise program as an example, and while the other group does not receive the treatment, and then compares the two in the end. Okay, so that's kind of background. Again, some of them might be slightly new terms as far as things you may not have seen in this course specifically, but the names themselves tell you exactly what we're talking about. Now, keys here to kind of how experiments should be done. And sort of wrote, traditionally studies have been done using essentially the scientific method. And one of the keys here is that to run a study in the past, to collect data was incredibly expensive, time consuming and expensive just to kind of go through the motion of getting people out on the street, doing the surveys, or watching the people do the work, whatever it happens to be. The way that we always did things was somebody had to develop a hypothesis first. The idea was we wanted to determine, we seem to think that such and such is going to happen, and we really believe that this, again, this medication is going to help people in the long run. And from that, we develop the study. We go through the process of collecting the data, analyzing the data, and drawing conclusions. And then, once the conclusions were drawn, we would release that information to the scientific community or the appropriate community, and they would look at the studies and try to reproduce them. If all that went through, then the study would be published. What's happened more recently is because computers are so inexpensive and so powerful now, and programs like spreadsheets and programming languages are there and can do data analysis at a very, very high level. The idea of generating or taking the data, let's say, taking existing data and analyzing it to start has become more popular. This is the concept of exploratory data analysis. And the idea would be that if I can just grab a bunch of data off the internet or from some other studies, I suppose, and mine through it, look for trends. But then the idea is that if I find what looks like potential trends, I would want to then go through the process of developing my hypothesis and studying it and checking it and so on. The problem is nowadays, one of the big problems with data analysis overall these days is because it is so easy to do, people who don't maybe respect the process quite as much as they should can do this as well. And instead of just kind of going from taking data and looking through it and finding something and then kind of developing a proper study to test their hypothesis or to verify the trends that they're seeing, people will sort of jump from step 0, or what I'm calling sort of step 0 being the using the data to come up with the hypothesis. They then jump steps 1, 2, 3, 4, ignoring the fact that it looks like this, but we should really test all that stuff, and they'd kind of jump right down to step 5, probably skip step 6 as well, and just kind of throw that out there as potentially the right answer at that point. A little bit of a rant, I suppose, in that. But the idea of analyzing data to start is not a problem anymore. It's just that it shouldn't be jumping from there to actually publishing something. We should be using that data to see what we can see and then follow it up by going through a proper study if we're actually going to try to publish it eventually. So what we're going to see in this next section is a few of the various tools that we may have available or we could make use of in doing some kind of a study. First one here, frequency charts or frequency tables. You might know them more as tally charts. Essentially just a listing where you've checked off the number of times something happens. So really simple, the idea of a frequency table is literally I've got a list of stuff here, some dates, I guess. These are the dates of birthdays for the students in the class. And so in order to make it a little bit clearer, I'm just going to go through the process of organizing it somehow. It seems reasonable to put them in order January through December, count up the number of times each value occurs, and eventually I could write it in as the frequency on the side. So just as I'm going through, I'm like, oh, here's a January, tick it off. Oh, there's a March. Oh, 2 Julys in a row. There's a September. And then kind of at the end, we're able to analyze it and then go further with it if we want. So that's all this is suggesting. Just if you see the words frequency table, when you hear the words frequency table, it is literally a table. I am telling you or suggesting how often something has happened, how frequent it is that January was the answer given. And of course, at the end, they sort of put the number in to make it just a bit clearer. In this case, the numbers were small enough that I could sort of look at it and see what the values were. But of course, if you had hundreds of values in each of these spots, counting them up at the end and having the frequency listed would make some sense. Of course, this could also be done in some kind of a spreadsheet or something if you had that, and then the frequency could just be counted. Those of you that did the Monte Carlo simulation have already kind of done that, right? We generated a bunch of values for the coins being flipped, and then we counted how often specific values came up, heads specifically came up, and then we counted up how often 3 heads came up or 0 heads came up, and so on. So while we sort of give the example here as if you had done it on paper, eventually, of course, that'll be done on some sort of computer at that point. So stem and leaf plots, kind of a second option. Stem and leaf plots will be used to organize our data for the sake of the actual analysis to come. So we'll try to look at an example and see if it makes it clearer. Basically, the idea here is that we've got 36 months worth of data. This is the number of times that rain fell during those months. Essentially the months, I guess it's supposed to be 30-day intervals, so it's not really by month, but same basic idea. In order to organize this, whoever was putting it together decided to separate into groups of 5 to 10, 10 to 15, 15 to 20, and so on. Now, I should note here, you do want to be careful with the wording here. It says 5 to under 10, so really this is 5 to 9 in this case, or 5 to 9.9 if it were dealing with continuous data. We won't use that terminology very often, and we'll see pretty soon how to write it in a more appropriate way. But that's the idea with that. So when we put it together, essentially the stem and the leaf separates a 2-digit number into 2 pieces, the stem being the first digit, the leaf being the second. In this case, the single-digit numbers would have a 0 almost out front, followed by their second number. So in order to just keep things organized and make it a little bit more visual, whoever was putting this together just went through and found there was a 6, an 8, a 9, and essentially said my stem of 0 has a 6, then an 8, then a 9, then again continuing across, another 9, then another 9, and just kind of listed them off in this section. Again, that then it's sort of a variation of the frequency chart in that not only does it allow us to count up how many values were in that range, but it allows us to actually have the data there with us in case we decide we want it afterwards. Okay, so last time basically you either chose January or you didn't. You chose February or you didn't. But in this case, in order to kind of keep things somewhat neatly organized, we've decided that putting together similar values makes some sense. We still have, again, an idea of how often the value was in that given range, but we do also have the actual data there for us. Stem 2 is the numbers between 10 and 15 essentially. So I see here a 12, the one out front with the 2, an 11, a 13, and so on. The numbers in the next range, oh sorry, yes, that was 10 through 14, I guess, because it was to under 15. And then same sort of thing here, we've got a 19, an 18, a 17, a 15, and so on. We've got the frequencies listed, but we have the actual data in case we ever want to have it. Quick note from Stats Canada and Leaf Plant. Well, from Stats Canada, stem and leaf plots. It says usually a stem and leaf plot is ordered, which means simply that the leaves are arranged in ascending order left to right. There's no need to separate the leaves with punctuation marks, commas, periods, since every leaf is always single digit. Okay, so I was going to suggest that as well. This is the one example where, I guess basically I just did it on the next line anyways. So it would be best to rewrite the stem and leaf plot in order so that it's, again, a little bit more obvious, and you can sort of see, again, you get a little bit more data from it. You see this nice grouping of, holy jumping, there's a lot of 17s, a few 16s, a few 18s. You kind of get a real feel for where the most popular values are. That later on will lead us to things like median and so on, median mode, which we'll get to in the next couple of sections. Now, there is example 3 here, a back-to-back stem and leaf plot. I think we probably won't see it again, but since it's in here, it's worthwhile mentioning it in case you do run into one. Essentially, a back-to-back stem and leaf plot is taking that, sort of that previous one and going a step further. It's allowing us to compare 2 similar sets of data. So in this case, we're comparing examination marks between the French and English classes. It says for 20 pupils, but obviously There were more than 20 pupils in the second group. So maybe I should fix that before you look at it. I don't know if I can though. Anyways, the idea would be the stem is again your first digit, and the leaf will be the subsequent digits. So just in order to organize it slightly differently and to have both sets of data there, we essentially put the stem down the middle, and then you can put the one leaf to the left, one leaf to the right, and I can see clearly the lowest mark in the French class was 31. The lowest mark in the English class was 38. The highest mark in English, 95. Highest mark in French was only 81, and so on. And you can sort of see pretty clearly again, you get the nice distribution that English marks generally lean higher, French marks generally lean lower, and so on. So again, you get the visual, you get the actual data values there, and you still sort of have a pretty accurate access to the count. If you wanted to, you could split this, of course, and have the actual frequencies off to the side as well, although it's obviously very simple at that point just to count them off if you need to. And then just sort of says some conclusions here. You can sort of see these things in the chart. Hopefully you can tell that is, as much as it might look a little strange, much easier to get information from than either of these sets of data where the numbers are just literally disorganized. Okay, so, and actually I guess I should say it at this point, that is what the word data means. Data is disorganized, kind of collected information, or collected data. I shouldn't even use the word information there. We start to call it information as it gets organized, because then it's sort of, it becomes more valuable. Data is pretty raw, just kind of here are the numbers. As we start to organize it, we're putting it together, putting it out as information. A couple more options here. Case tables, that you know as spreadsheets. And I don't think there's anything I really need to go through there, just they're organized sets of data. The one thing I would say, when we use spreadsheets, we always list downward and across in this way. So if you have names or individuals, they come down, and you have multiple values for those, go across. I've seen a number of people in the past kind of, when they had to put things together, try to organize it differently, and the computer automatically assumes this kind of layout. So just sort of use those as reference if and when you end up doing some kind of spreadsheets. There'll be more information obviously when you do, but at the same time it is important that it's organized that way, because visually it just makes a lot more sense. I can see Corey Perry, and there's the information for Corey Perry. I can see Rob Shrimp, there it is. It's just not quite as clean when we go the other way. Last couple here, what do we got left? A few more, I guess. Bar charts, bar graphs, probably nothing I need to say too much about this. Bar graphs are just the frequency distribution, so it just sort of shows how often did various values come up, or various options come up. I don't think there's anything that needs to be discussed there really. Pictographs, similar again, kind of like well, this one isn't, but a prettier looking bar graph. Essentially, you use some kind of image in order to display the number of times something came up. So again, it's basically a bar graph where maybe you're using soccer balls to represent the number of people who participated in soccer in your town, or town to town. In this case, it says X represents 1,000 people, so these are the number of people who in those areas who own an Apple computer. I probably would have been smarter to put an Apple in there, except maybe I couldn't actually edit this picture, and I just didn't take the time to do so. And then the last variation here is the histogram. It is essentially a bar graph, but it is a bar graph on continuous data. Okay, so this is sort of the key. When you have, so if you remember, two terms that maybe I should add to the top of the page: discrete data versus continuous data. Discrete data is the numbers have to be integer values, so it's counting data. So anytime if somebody asks you your age or your grade, is a better example. You're in grade 12. You might be in grade 11, but you're not in grade 11.33. You're not 11 and a half. Sometimes people do say that for age, so I try to get away from that example. When we talk about height, I might say I'm 5'9". I might say I'm 5'9.5". I might say I'm 172 centimeters. But if you had some kind of more accurate measurement, you might find that I'm 171.8. And if you got more and more, if you found more and more accurate measurement tools, you could go decimals further and further. So essentially, if the values you're talking about can be decimal values, it's what we call continuous data. With the idea that if 0.9 is a legitimate answer, then 0.99 is as well, and 0.9999999 is as well, and then at some point it just turns over and it becomes the next number up. So it's now 1, let's say. And then at some point you get 1.9, 1.99, 1.99999, and then 2. But there's no gaps between the values. Just all of a sudden you go to the 2 and you move forward at that point. So again, that's what continuous means. So in this case, we're looking at heights for students in the class. I guess this is my first class from 1967. So there were 8 people in the range 150 to 155. So this is the standard we use for representing that. The square bracket means the value is part of the group. The round bracket means the value is not part of the group. So essentially this first grouping here is any height between 150 centimeters and 154.999999999 centimeters. If somebody measures 155 exactly, they've been rolled into the second grouping here. And again, we continue with people in this group all the way up to 159.9999999, and then at 160, they roll into this grouping. Okay, so again, this is the syntax that we'll use moving forward. We'll avoid what it said above with 10 to under 15 sort of ideas. This will be the standard we use. And because the data is continuous, when we draw our bar charts then, we get what we call a histogram. And the histogram basically just doesn't have gaps in it. So again, it's exactly the same as a regular bar chart, except that it has no gaps, and we draw it without gaps because we want everybody to understand that the second you hit the 155, you've gone into the second bar. The second you hit the 160, you've gone into the third bar. And again, there are no gaps, indicating that there's no space that's not being covered by somebody in our group. If it turned out that there was, for whatever reason, nobody in group 2, it's fine to have a 0 there, and in that case we would have a gap, although it would be a gap only because there's nobody in that group. It would be a gap on the screen, but we would still have it covered in the bottom. And then I guess very last comment about that, so this kind of took a little longer than I intended. There's a video down here about building the histogram. You can worry about that when you get to having to do one yourself. Essentially when we're doing this, we're going to try to pick values for these that will give us something in the range of, so what I write here, at least 5 and no more than about 12 bars on our histogram. And again, that's kind of, I'm making up a general idea, but when you do this, you want to have enough different options or different groupings that you can see some kind of a trend, but not so many that it's overwhelming. So again, 5 to 12 will be the answer if you're ever asked how many, what is a reasonable number of bars on a histogram. But to some extent, you're going to choose A, what's kind of convenient, and B, what makes sense. Note, there's no right answers to what our bin width should be. So this is me kind of babbling through this last section. We'll use our best judgment and determine what is reasonable. In the video, I could definitely have chosen 10. Oh, so that's referring to the video here. So I said I could have chosen this, but I wanted to show the math. So what I did in this case was I went through and chose a slightly less convenient number to kind of go through the math to make sure that you sort of saw how to do it. But the basic idea is, we're going to choose what makes sense for the sake of the work we're doing. So I'm going to stop there. It'll get to be quite a long video, I guess, but hopefully I might have cleared up a few things along the way and saved you sort of reading through it all on your own anyways.